We all know AI is absolutely amazing at understanding the 2D world. Photos, videos, all that stuff. But what happens when we ask it to see the world like we do, in 3 dimensions? Well, that leap from a flat picture to a full 3D space is one of the biggest, most fascinating challenges in AI today. And we're going to break down exactly how researchers are teaching machines to finally see in 3D.
Okay, so think about it like this. On the left, you've got what AI has totally mastered, a 2D photo. For a machine, it's just a simple, flat grid of pixels. Easy. But on the right, that's a whole different beast. A 3D medical scan isn't a grid of pixels, it's a volume of voxels. It has real depth, real structure, and that's something a 2D model just can't wrap its head around.
And that leads to the really big question. Why is this so ridiculously hard? Well, it all comes down to computational cost. See, when you go from a 2D square to a 3D cube, the amount of data doesn't just double or triple, it scales cubically. Even a tiny increase in resolution causes a massive explosion of data that can totally overwhelm our most powerful models.
This enormous computational problem is really the heart of AI's 3D vision challenge. And this is right where our story of some seriously clever innovation begins.
So when you're faced with a tough new problem, what do? You grab the best tool you already have, right? And for 2D vision, the undisputed champ is the Vision Transformer, or VIT. So researchers started with a pretty simple idea. Can we just, tweak the 2D VIT to handle 3D data? And that impulse led directly to the very first attempt at a solution, the 3D Vision Transformer, or as we'll call it, the 3D VIT.
So a 3D VIT is pretty much exactly what it sounds like. It takes that powerful self-attention mechanism, which is how a model figures out which parts of the data are most important, and just tries to stretch it to work on 3D inputs, like a CAT scan or the point cloud data from a self-driving car.
The way they do it is actually pretty straightforward. You take a big 3D volume, say an MRI, and you chop it up into a bunch of smaller 3D cubes. They call them volumetric patches. Then you take each one of those little cubes and you just flatten it. You stretch it out into one long line of data, turning it into a token that a regular transformer can understand. It's a clever way to fit a 3D peg into a 2D hole, but it creates a really big problem. And this is where things get super interesting. This simple adaptation, while it seems smart on the surface, leads to a deep, fundamental flaw we're going to call the lost in space dilemma. To get what's going on, let's look at a similar problem with language models. As this quote points out, even these huge LLMs can get tripped up by something as simple as counting. Why? Because a standard transformer can sometimes treat a sentence like a bag of words. It sees what words are there, but it loses the crucial sense of where each word is in the actual sequence. And that is the exact same problem that happens to the 3D VIT. By flattening those 3D cubes into one long single-file line, the model loses all sense of spatial relationships. It sees every single patch of a brain scan, but it has no idea which patch is in front, which one's behind, which one's on top or on the bottom. It is, quite literally, lost in space.
The fix for this problem is a really cool concept called positional encoding. Honestly, the best way to think about it is like adding a little GPS coordinate to every single piece of data before it goes into the model. This extra bit of info tells the transformer not just what the data is, but where it is, giving it that sense of order it was missing.
Now, there are a couple of basic ways to do this. Absolute position is kind of like a street address. It says, this is token number 127, period. It's a fixed, unique location. Relative position is more like giving directions. This token is 3 steps to the left of the one I'm looking at right now. It's all about the relationship between things. Both are useful, but for complex 3D space, we need to get even smarter.
So that whole lost in space problem, it actually kicked off a huge wave of creativity. Researchers figured out they couldn't just tell the AI where things were, they had to teach it to understand spatial context. One of the first really big breakthroughs here is something called bilevel positional encoding, or BPE. It's a brilliant idea because it understands that data has a natural structure, like a book, so it uses 2 levels of position. Level 1 is for your position within a sentence, and level 2 is for which sentence you're in. It's a much more natural and powerful way to describe where something is. Then there's another genius method called contextual positional encoding, or COPE. This approach says, hey, maybe not all tokens are equally important for figuring out your position. So the model actually learns to decide which other tokens are relevant. The final position isn't just a simple count anymore. It's a count of only the tokens the model decided actually matter. All of a sudden, position isn't a fixed address. It's dynamic and aware of the content around it.
So the big question is, do these clever ideas actually work? Oh yeah, the difference is just staggering. On complex tasks that really depend on order, like arithmetic, a model with standard positional encoding might get it right about 70% of the time. But when you add in these advanced methods like BiP and COPY, the accuracy just skyrockets to 97%. They give the models the spatial reasoning they were so desperately missing. So we have our solution, right? Smarter positional encodings. Problem solved. Well, what if I told you another group of researchers looked at this whole big problem, the scaling, the complicated math, and just decided to skip it entirely? Yeah, this is where our story takes a really wild turn. This is the crazy, provocative question they asked. Is it even possible to get world-class 3D vision without ever doing the expensive, complex, time-consuming work of actually training a 3D model from scratch? Their answer is a method they call Raptor. And the most important phrase you need to hear is train-free. It's a completely radical approach that creates these incredibly detailed 3D representations by basically piggybacking on the giant 2D vision models that we've already trained on billions of images. Okay, you have to hear this process because it is so clever. First, they take a 3D volume and just slice it up into hundreds of regular 2D pictures from every possible angle. Top down, side to side, you name it. Then they take a powerful, pre-trained 2D model, and they don't retrain it at all. They leave it frozen and use it to analyze every single one of those slices. This creates a mountain of data. The magic happens next. A slick math technique called random projections compresses that entire mountain down into one small but incredibly rich signature of the original 3D object. And the results? They are just mind-blowing. This chart shows Raptor, with zero 3D training, remember, going up against other state-of-the-art models that were painstakingly trained on huge 3D medical datasets. And Raptor doesn't just compete with them, it beats them. It outperforms these specialized 3D models by anywhere from 3 to 14%. It's an incredible win for this totally out-of-the-box approach. So, wow, what a journey, right? We started with this problem that seemed almost impossible, and we ended up with two completely different, totally powerful solutions. So, where does that leave us? What's next for 3D AI vision? Let's just quickly recap the big takeaways. First, we learned the Core 3D challenge wasn't just about bigger data. It was about the AI being completely lost in space. Second, brilliant new ideas in positional encoding, like BPay and COPay, gave these models the sense of direction they needed. And finally, the ultimate plot twist, methods like Raptor prove you can solve 3D problems by just getting really clever with the powerful 2D tools we already have. And that brings us to the final thought. For years, the third dimension was this fuzzy, out-of-focus world for AI. But now, with these incredible new tools, it's all coming into sharp relief. From mapping the tiniest pathways in our brains to navigating our complex world, the barrier has been shattered. The question is no longer if AI can see in 3D. The real question is, what profound, invisible worlds will it help us discover now that it finally can?